Welcome to the lesson on tangents to a circle. At the end of this lesson, you will be able to define a tangent to a circle and prove that a tangent to a circle is perpendicular to the radius of the circle drawn at the point of contact. You will also be able to prove that tangents drawn to a circle from an external point are equal in length. Have you ever noticed the wheels of a vehicle moving on the road? What does the surface of the road look like against the wheel? Does it look like a line touching a circle at one point? Well, this is what you call a tangent. Here are a few more lines. Are all these tangents to the given circle? Let's find out. Observe this line. Note that this line does not touch the circle at any point. Thus, it is not a tangent to the circle. Now, what about this line? This line touches the circle at 2 points. This line isn't a tangent to the circle either. A line that touches a circle at 2 points is called a secant of the circle. Observe these lines. Each of these lines touches the circle at only 1 point. A line that touches a circle at only 1 point is called a tangent to the circle. The point where a tangent touches a circle is called its point of contact. Here P is the point of contact of tangent AB with the circle, and Q is the point of contact of the tangent AC with the circle. Here is a circle with a point P marked on it. How many tangents can you draw to the circle at the given point P? We can draw an infinite number of lines passing through this point. But are all these lines drawn through the point P tangents to the given circle? As you can see, all these lines touch the circle at 2 points. They are secants, but not tangents to the given circle. Now observe this line. This is the only line that touches the circle only at 1 point. This implies we can draw only one tangent at any given point on a circle. Here are 3 friends, Mr. O, Mr. A, and Mr. B. While Mr. O is standing at the center of a circle, Mr. A and Mr. B are standing on a tangent to the circle at point P as shown. Mr. O thinks that if he walks straight to point P, he will meet Mr. A and Mr. B at right angles. Let's see if this is true. To verify Mr. O's claim, we have to verify the theorem that states that the tangent at any point on a circle is perpendicular to the radius drawn to its point of contact. Here we have a circle with a tangent AB drawn to it at point P. OP is the radius of the circle. Now we have to prove that OP is perpendicular to AB. Now consider another point C other than P on the tangent AB. Can point C lie on the given circle? Certainly not, because if C lies inside the circle, then the line segment AB has 2 points of contact with the circle, which contradicts that a tangent has only 1 point of contact with the circle. Thus C must lie outside the circle. Now compare the length of OC and OP. Which do you think is longer? OC is definitely longer than OP, since point P lies on the circle and point C lies outside the circle. This is true for all points on the tangent AB. Since OC is longer than OP for any point C on AB, we can say that OP is the shortest distance between point O and the line segment AB. Now the shortest distance of a point from a line segment is the perpendicular distance of the point from the line segment. Thus OP is perpendicular to AB. Hence the theorem is proved. So Mr. O was right after all. Meet the great explorer, Mr. A. On his expedition, his path is blocked by a huge circular crater. Mr. A has to find a way to go past it. Now, being a man of great courage, he doesn't want to be too far from the danger, so he wants to go across a path that is at tangent to the crater. How many such paths are possible? Actually, there are just 2. As you can draw only 2 tangents to a circle from any point lying outside it. So Mr. A has the choice of going along either AB or AC. Which one should he take? Which route is the shortest? Let's find out. To help Mr. A make up his mind, let us prove the theorem that states tangents drawn to a circle from an external point are equal in length. Here we have two tangents AB and AC drawn from an external point A to points B and C on a circle. We have to prove that AB and AC are equal in length. Let us start by joining the external point A to the center of the circle O. Now join OB and OC. Here OB is perpendicular to AB. Since the tangent at any point on a circle is perpendicular to the radius drawn to its point of contact. That is, angle OBA is equal to 90 degrees. Similarly, angle OCA is equal to 90 degrees. Now, in triangles OBA and OCA, angle OBA is equal to angle OCA, which is equal to 90 degrees. OB is equal to OC, since they are the radii of the same circle, and OA is a common side. Thus, triangles OBA and OCA are congruent by the RHS congruence rule. Since triangles OBA and OCA are congruent, AB is equal to AC, as corresponding sides of congruent triangles are equal. Hence, the theorem is proved. This also means that Mr. A can walk along either AB or AC. He will be covering the same distance. You have reached the end of this section. Before moving on to the next section, let's recap the key points covered. The tangent at any point on a circle is perpendicular to the radius drawn to its point of contact. Tangents drawn to a circle from an external point are equal in length. Hope you enjoyed your learning experience.